Albert Einstein famously said that he didn't believe God plays dice with the universe. But there is another related, even stranger aspect to quantum mechanics. In classical physics, external reality is independent of the observer. Looking at the moon doesn't change the moon. And if you look away, the deterministic laws of physics continue to guide the moon on its path. But in quantum mechanics, things are weirder.
The basic idea of quantum mechanics, the thing that we really struggle with to get our heads around, even as professional physicists, is that unlike any other version of physics, quantum mechanics separates what happens in a system when we're not observing it from what we see when we measure it.
A few rare exceptions aside, quantum mechanics says that we can't know the position of a particle like an electron when we're not observing it. At best, it can only be described mathematically as a wave, its exact position given in probabilities. But at the moment that the particle is observed, the probabilistic wave function collapses to one specific location. To the observer, who never sees this wave-like quality, it is like the particle was a particle all along.
That opens up a whole world of questions. What happens to the observational outcomes that are not observed? What picks out which outcome is going to happen? This is still what we're thinking about today.
During that mysterious period, when the particle is considered neither here nor there, it is said to be in superposition. In a sense, a combination of all the possible outcomes. But what does that really mean?
Is the electron everywhere at the same time? Is it nowhere at all? Is it at one place and we just don't know? All of those questions are actually outside of what quantum theory itself actually can answer. It's not part of the theory at all. So if you ask me, your guess is as good as mine. Unfortunately, that's the best I can do.
For most people, quantum mechanics remains deeply unintuitive. And yet, it has proven itself again and again by making predictions with uncanny accuracy. In practical terms, it is the most successful theory science has ever produced, and it has shaped our modern life.
Quantum physics has not just been important, it's been revolutionary. It's completely changed the way we used to live into the way we live now.
Take our sense of time. Perhaps there is no better illustration of our intimate relationship with it than music and dance.
The underlying movement of tango is reliant on the beat, which is reliant on timing, which creates synchronization. To create a truly smooth dance, it's not enough to just be synchronized on the beat. It's also the synchronicity between the beats that's important. That's the real beauty in it, in finding that connection through stretching out that second.
Tara Fortier is a tango professional and a physicist deeply involved in the science of time.
So we have a number of systems in this lab.
She works here.
These systems are used to characterize atomic clocks and also compare atomic clocks.
At the Boulder, Colorado laboratories of the National Institute of Standards and Technology, or NIST. Home to some of the atomic clocks that help set the official time for the country. Over the centuries, we've tracked time a variety of ways. By the sun's movement, the swing of pendulums, the oscillations of springs, and in the 20th century, the vibrations of quartz crystals. But since the 1960s, time has been officially determined using atomic clocks and the quantum characteristics of atoms.
And the idea is that the laws of physics are unchanging. Unlike something like the rotation of the Earth itself can change because of plate tectonics, because the moon is moving away from the Earth. Its physics is not truly fundamental.
The reason why we love atomic clock, it's a universally defined time. No matter who does the experiment, no matter where you do the experiment, in principle, once you corrected for all the systematic effects, it should produce the same time, no matter where.
The consistency of atomic clocks arises from the very nature of atoms.
Atomic clocks depend crucially on the quantum physics of atoms. You have a nucleus around which there are electrons in certain energy levels. And these energy levels are possible energy states that the electron can have inside the atom.
Since an electron can only be at certain energy levels and not in between, to get to a higher level, it needs to encounter a very specific helping hand, such as a particular photon.
So if it were to absorb an incoming photon, it would have to be of just the right energy to jump from one level to a higher level.
That special relationship between the electrons of a particular atom and a photon of a specific energy level is a unique signature for that atom. It's called a resonant frequency.
So this characteristic signature of this atom gives us a very specific frequency standard that we can use to build a timekeeping device.
Atomic clocks work in different ways, but they all use a specific type of atom or molecule as a reference to lock in the frequency of an electromagnetic wave, whose oscillations provide the ticking of the clock. Today, a second is officially defined by counting the oscillations of the primary resonant frequency of a cesium-133 atom. That's over 9 billion oscillations per second. And you interact with that time reference more than you might think. For example, through the Global Positioning System, GPS.
Turn left. I think that GPS is actually kind of crazy when you think about it. How did we do anything before GPS?
The US-based GPS system uses over 30 dedicated orbiting satellites, each with multiple atomic clocks. When you use the GPS on your cell phone, its receiver checks the signals from 4 or more satellites. The signal contains information about the satellite's position and the time it sent the signal. That timestamp is critical. Your phone uses it to calculate how long it took to receive the signal, and from that, knows the distance to the satellite. With that information from multiple satellites, it is possible to triangulate the phone's position within a few yards. But the whole system depends on knowing the time.
In the end, I find it amazing how strongly we're committed and tied to atomic clocks and how much we take it for granted.
Even though I build atomic clocks, but when I'm driving, being guided by this GPS service, you don't really become aware of how much atomic clock technology has permeated everywhere in modern life. Have you had a chance to look at more systematically varying the BZ?
Jun Yi is a physicist with joint appointments with NIST, the University of Colorado Boulder, and their joint institute, GILA.
What if you lock exactly on top of each other and see whether that peak disappears completely?
He works on the new generation of atomic clocks, known as optical atomic clocks. While cesium clocks use microwaves, optical clocks use lasers, which run at higher frequencies. That also means using a different atom. Instead of cesium, June's work mostly uses strontium atoms, along with a laser carefully tuned to one of strontium's resonant frequencies. It puts one of the strontium electrons into superposition, so it is both excited and unexcited at the same time, creating what June calls a quantum pendulum.
This pendulum is swinging at a speed of nearly 1 million billion cycles per second. It's going back and forth, and this superposition creates this quantum pendulum.
And when it comes to accuracy, more swings or higher frequency equals more precision. If you think of swings as marks on a ruler, the more marks you have, the more exactly you can measure. So compared to a cesium clock, June's strontium clock is around 100,000 times more precise.